We're now going to hear from Professor Stephen Russell, who's director of the Leeds Institute of Textiles and Colour, part of Leeds University. And Steve's going to give us a brief glimpse into a possible future. We've heard from companies and specialists about ensuring their processes are certified, and the 101 publication offers a guide to the certification of fibres that we know about. But what about future materials? What new fibre types are being developed? How will they offer practical, sustainable alternatives to cotton, wool, and so on? So Steve, can I ask you to come up and present? Thank you.
Thank you very much, Adam, and good afternoon, everybody. I'm acutely aware that I'm an academic and I'm stuck between you and coffee, so I will do my best. I'm also a technical person, so you'll forgive me if I do stray into the technical world a little bit. But what I want to do today is give you a perspective. I'm not here to advocate a future. I'm here to just give you a perspective on how things might develop, particularly around navigating the practicalities of manufacturing, bearing in mind we have installed capacity right now, and the need to meet emission targets by a mandated date. All that in half an hour or so, fingers crossed. I mentioned manufacturing. That's why many of us are here today. Many of you in the room today are manufacturers. I'm going to talk a little bit about the rise of recycled content and how that might develop. There's a lot of talk about recycled polyester. I know many of you know. Most of that doesn't come from our industry. It comes from the packaging industry. And I'm not sure how long that will sustain itself before we need to think about using our own waste a bit more. And I'm also going to just be a bit provocative and lay out a scenario where we could potentially all be heroes, where man-made fibres might be sucking greenhouse emissions out of the atmosphere, CO2 out of the atmosphere, as we try to get nearer to net zero. But there are some conditions for that, naturally. So let's have a look at how heavily the tap is running. I'm taking quite a global perspective in this presentation. I think it's important. Yes, we don't make a lot of fibre in this country, but we consume a lot of it, and a lot of the waste ends up in this country as well. We're roughly at 120 million metric tonnes per annum, which is nearly a third of the weight of all humanity per annum. It's like dragging a bag of a third of your body weight around every year. That's how much we're producing. And what I'm not going to talk about today is a beauty contest between one fibre or another, because the reality is, regardless of how we make our fibres, we can make them in less damaging ways or more damaging ways. We have to process them, we have to manufacture them. And if we're burning fossil fuel to do that on a large scale, then it's fairly predictable that our GHG emissions aren't going to look too clever. We don't do particularly well at collecting those materials at the end of life either. And that material is a potential feedstock, but it also has sequestered carbon in it as well, if it's natural fibre, for example, which if we burn, goes straight back up into the atmosphere. So we do need to think about things end to end, not just the first bit. So let's have a look at how we got to where we are now. I've kind of come up with these generations for my own entertainment, so if anyone disagrees with them, email me later and say something uncomfortable. But for hundreds, thousands of years, we've relied on natural fibres. And then all of a sudden, in the late 1800s, then into the 1900s, we realised we could take those natural resources and make man-made fibres initially, leading to viscose, so that's regenerated cellulose from plants, basically, and then moved into the period in the 30s and 40s where we invented synthetic fibres, these wonderful miracle materials. And I live in Harrogate, back of my house overlooks where ICI used to be, with Crimplebeck running a little bit further away. I understand Crimplebeck and Crimpline are in some way linked. Anyway, that's irrelevant right now, but I thought I'd mention it. And there's a few timeline things on there. You can see that some of our fibres that we think of quite new, like polylactic acid, PLA, they're actually invented, the chemistry was invented a long time ago. It's just that we've only more recently started to use it. And now we're into this era of recycled content. And that recycled content also could be biological waste, particularly agricultural waste, biomass, as well as polymer waste from our own industry and from others. So we started with natural materials, we then invented synthetics, now we don't like them and we want to go backwards. Unfortunately though, we are where we are, so let's be realistic. Another big diagram. I don't expect you to read all of those, but it's really just another way of saying what I've just said. But the point is, we are making fibres today from all of the feedstocks on the right-hand side, and we could do that a lot more than we are doing. But fundamentally, we're dependent on the ones bottom left, coming from fossil fuel sources. So we're extracting fossil fuel, we're turning it into synthetic materials, using it for a while, and then chucking it away. By the way, many of those chemistries are actually quite recyclable if we collected them. So it doesn't need to be that way. But the elephant in the room, ladies and gentlemen, is despite all of this talk about sustainability, our dependency on synthetic polymers is increasing, not decreasing. Okay? Globally. So we are, these, you can see the trend here, and it doesn't look like it's going to level off in the coming years. So there's a really big question to ask. If we're so dependent on these materials, realistically, what can take their place? And this is where I want to get practical. If I can remember my slides, which as a typical academic, I can't, I have to keep looking left. So apologies if I'm looking left too much. It's not that I'm shy, it's just that I need to see what's on the screen. So first of all, this is by no means a full list of some of the considerations, but there is no point making fibres that don't have physical properties that make products work. There's no point making fibres that aren't compatible with installed manufacturing infrastructure. It's literally academic, right? So I don't think the world is mushrooms. It's not completely mushrooms anyway. And then of course we have economics. Now economics is an interesting one because economics depends on the playing field. If we have no incentives for doing the right thing, for recycled content, for not being so carbon intensive, it's going to be a hard ask for people to pay more just because they want to do the right thing. So the playing field with extended producer responsibility, with financial incentives, financial disincentives, I think is going to be necessary to really accelerate the change that we need to see. So let's see how that develops. The other point I wanted to mention is the installed capacity. These are the three main methods that we make fibres with, man-made fibres, okay? And the vast majority require the polymer to melt. If the polymer doesn't melt, viscose doesn't melt, cellulose doesn't melt, we can't spin it into filaments. We can't make man-made fibre. 65% of the installed capacity or thereabouts requires the polymer to melt. Once we've done it, the fibre we've made has to have basic physical properties, or again, we're stuffed in terms of manufacturing, because the fibre will not go through the processes we need the fibres to go through. So compatibility with the process and physical properties that are relevant are critical. And it's the same in the non-wovens industry, technical textiles. Roughly 94,000 tonnes of non-wovens are made in this country alone, every year, on three main platforms. The first one is 100%, has a 100% requirement for melt spinnable polymer. That's the technology to far left that we all depended on during COVID. All the PPE was made using those processes. The middle one and the last one also run with polyester staple fibre, polyamide staple fibre, polypropylene staple fibre, and natural fibres as well. So it's not just the traditional textile industry, it's also non-wovens. So a very logical question to ask is, we need to start capturing a lot of this material that we are using, the synthetic polymer material, including polyester. Again, contrary to popular belief, polyester is actually quite recyclable, and it can be recycled more than once. I heard somebody mention earlier on, you can only go through once, but actually technology is developing. Even thermomechanical recycling now allows you through, for example, liquid state polycondensation, to build the polymer chain back during the recycling process and then directly re-extrude. So what you extrude has the same physical properties as what you fed in. Okay? So that the technology is developing rapidly. So we can do this stuff, but we need to be collecting and recycling using appropriate methodology, and we need to be not falling into the trap of making recycled material that doesn't have the right physical properties for a fibre to function. And I just wanted to point out the importance of the ACT initiative that UKFT is leading, because sorting is critical for these processes to work properly, to get the right feed streams to be fed to the right recycling processes. That's fine. Let's look, if my memory serves me right. And it doesn't. This is just another one. Just wanted to mention. You can tell I put this together in a hasty fashion. We are developing other technology as well to aid recycling. So many of you will know that these recycling processes have a degree of tolerance for impurity, but there is a limit. So colleagues at Leeds and elsewhere are developing technologies to get dyes and other auxiliary chemistry out of the polymer using low-cost technology so that the polymer can be recycled more easily. So this is one where we modify the dye that is used to dye polyester, dispersed dye, so that it absorbs CO2. That makes the dye soluble. It goes into the polyester, and then we reverse the solubility so the dye stays in the polyester. Then we want to get the dye out. We use pressure and heat and CO2 to strip it back out again. And then you can recycle the dye and the polymer separately. So remember, if you don't think about it that way, you'll have loads of sludge, other stuff over here, as well as the polymer. You need to recycle everything if possible. So these are the sorts of technologies which are being developed, and Richard and his colleagues won the John Lewis Partnership Circular Future Fund last year to develop this, and it's now scaling up. This was the slide I was remembering. So, after recycled content, this is the provocative section of my presentation. What next? Given we're so dependent on fossil-based polymer material, could we create bio-based synthetic man-made fibres that could replace fossil-based fibres such as polyester and even sequester CO2 in the process to reduce the amount of CO2 in the atmosphere? Potentially, yes. Particularly if the fibres we make have the same physical properties as the fibres we're replacing. So imagine making fibres that have identical properties to polyester, identical properties to polyamide, nylon, and are also compatible with the same recycling systems, but are bio-based, not fossil-based. They'll go through our processes, they don't muck up recycling, we can have our cake and eat it, potentially. Now, the basic strategy, just a few introductory slides, is to think about this. Rather than using oil refineries to make our materials, we use biorefineries. So you take an agricultural feedstock, but you don't take a food feedstock, so you don't compete with food consumption. You use this up to 70% residue that is wasted by food production as a feedstock to make these materials. Okay, so from memory, I think in the growing of corn, the stover that's left over is 70% of the plant. But that is bio-waste that we can use as a raw material, and we can use hydrolysis or fermentation to get chemistry that makes us an exact copy of fossil-based polyester. We could also use waste cotton. Right, so let's have a bit of an overview think about this. So 2 products. Picture their at the top, me 25 years ago. And obviously that's a wearable hygiene product, shall we call it? It doesn't last very long, made of textiles. And then there's a more durable product we would like to think underneath. Now, contrary to popular belief, you can make compostable thermoplastic polymers both from fossil-based sources and from bio-based sources. Okay, now, if you're going to make a compostable product, is it more sensible to make the compostable baby's nappy, or is it more sensible to make a compostable item of clothing? Or is it in fact more sensible to build it so it's recyclable, the clothing I mean? This rational decision making about what polymers you're using. If you compost or biodegrade, you put CO2 emissions up in the air. And if it's mixed with waste, organic waste, it could be worse. It could be methane if it's in a landfill site. So the idea that biodegradation and compostability should be the destination is potentially questionable if what you're doing is putting CO2 emissions up in the air as a result. Perhaps it's better to keep it going in circulation. Now those little green arrows underneath are just there to remind us that if we use bio-based sources, we've sequestered as part of photosynthesis, CO2 from the atmosphere to grow the plant. So part of the CO2 in the atmosphere has been sucked out by the plant to grow the plant, and now if we're careful, it forms part of the fibre. That CO2 gets released if we burn the fibre again. Yeah? If it doesn't degrade, it doesn't do very much. It just sits there in the ground, but it doesn't emit, potentially. So these are all considerations. Now, clearly I mentioned earlier on that if we think of these synthetic materials as resources, we can now go a step further, because a bio-based thermoplastic that is recyclable, doesn't degrade easily, has sequestered carbon dioxide inside it, is now a feedstock that we can use again. And if we use it again in an appropriate way, we don't release all of the CO2 back. So we're gradually sucking CO2 out of the system. And what some very clever polymer scientists are saying is, if we're worried about technology for recycling, if the material doesn't degrade, let's store it as a resource for the future, like a neo-fossil. So that black stuff in the ground that we call oil has been there for millions of years, thousands of years, millions of years. We figured out what to do with it. The tap that's flowing synthetic polymer out at the moment that we're not collecting is a resource. Our technology is trying to catch up. If we collected it, didn't let it degrade, it's a resource for the future. That's the thinking. Neo-fossil. I have to thank Tony Ryan at Sheffield University for that phrase. Right, I bet you all look forward to this slide. So here, I'm just giving you a bit of an overview. I don't want to spend too much time here because it's a bit busy, but the point is, where I've put the red stars, those are all polymers that we can spin into fibres using melt spinning. And the ones at the bottom left that you can see those very large companies sniffing around are all identical to the fossil-based equivalent. They are physically identical, structurally and chemically identical. No compromises from a property perspective. And you can see that a little bit more clearly here, that we call them drop-in chemistries. So instead of taking the fossil-based source to make the terephthalic acid and the ethylene glycol that we need to make the polymer, polyester, we get the same chemistries but via a different route. We just have to be very, very careful how we make those monomers so that we're not using more resource than we would have done using the fossil-based route. Okay, so the source and the actual process needs to be carefully looked at. And this particular example is for bottles, but you can do similar calculations for textile materials. The thing to look at here is all of those bars that you see are different routes to getting to biopolyester material product. Okay, so this is assuming the product is not incinerated and the feedstock is a second generation feedstock, i.e. bio-waste, not a food source. And the numbers get even more attractive if you do this with renewable energy. Don't burn fossil fuel, please. So look here at the black spot. And you'll see on the third one along, the black spot is getting very close to zero, GHG, over the life of the product. And that's because of all the sequestered CO2 inside the polymer, which is the green bit. So that's the CO2 that's been collected by the polymer during the growth of the feed of the raw material, which is now kind of embedded in the fibre, if you like. The other point about this graph is why I don't like beauty contest between fibres, because it all depends on exactly how you make it, right? There is no such thing as one type of viscose. It depends where you make it, how you make it. You've got to be very, very careful about those sorts of comparisons. You can see here exactly the same material, bio-PET, made in, 5 different ways, 5 different results. I bet you're looking forward to this one. The only reason I put this particular one up was just to show that in addition to those drop-in plastics, there are also unique bioplastics that can only be made from bio-based materials. And PHAs, polyhydroxyalkanoates, are getting a lot of attention from the the short life products, so things like baby diapers, that sort of thing. Those materials are getting a lot of attention because they are recyclable as well as being melt spinnable. And the capacity is ramping up. And just an example of those PHAs. This is a colleague at Leeds, Giuseppe Tronchi, taking food waste, in this case coffee waste. And what these bacteria do is, effectively, it's a sort of biofermentation process where PHAs are a form of polyester, actually. And the bacterium stores polyester granules in its cell lining. And then you can extract that polyester in the form of granules, melt it and spin it, or in this case, wet spin it with dye, and then use the same basic approach to have a closed-loop recycling process. So making polyester entirely from food waste. There are some challenges, the 5 E's. I mentioned the fact that where the source of the material comes from is really important. There is also an economic penalty in terms of drop-in chemistry, so you'll see there roughly 30% more expensive for bio-PET, last time I looked, compared to fossil. But this is where incentives and disincentives might come into play, of course, isn't it? And actually, although I've mentioned there that recycling streams are yet to be established, that's not the case with bio-PET because it's chemically identical to the fossil-based equivalent. Very small at the moment in terms of volumes, but it's increasing rapidly. PLA is the largest at the moment. Bio-PET is only roughly 0.5% of all the polyester we're making today, but I think we might see that increase in due course. And finally, students like it when I say that normally. I think one of the previous speakers mentioned man-made cellulose, regenerated cellulose fibres, and how, as many of you will know, they are produced mainly from wood pulp. And one of the major areas of development is to substitute the wood pulp with other sources of cellulose, and that could be waste clothing. But remember what I said before? This technology isn't compatible with 65% of our spinning capability, right? So we can't just switch to this and expect it to do everything. It fills a need, but it can't take over unless we want to completely disrupt our manufacturing infrastructure. But we also need to be careful. So I've just given one example here. Infina was mentioned actually, I think, by the previous speaker. This is a little greenhouse gas emission comparison by Paunanen, who came to see me quite recently for a few months. Had a few research discussions about various things. But look at the life cycle assessment impacts for global warming potential for this new fibre. It's not bad, but it assumes that the energy and the way that the fibre is produced is all in the developed world, in modern conditions, shall we say. If it isn't, then the picture doesn't look as rosy. So this is the other point. While we need to get past marketing and look at this from a scientific, evidential perspective. It all depends, but it's not impossible. But just because something's recycled doesn't mean necessarily it's good. We just need to look at how we're doing the recycling. Okay, so this is my summary slide, although there is one after this. It's not a funny slide, don't get too excited. But the first thing is clearly in the short term, we are wasting huge amounts of valuable feedstock called synthetic polymer. The problem with synthetic polymers isn't the fact that they're called plastics, it's the fact that we let them leak. There's nothing fundamentally wrong with them other than we making them from fossil fuels and we let them leak. We've got to stop that and use them, treat them as a feedstock resource, and then gradually, as quickly as possible, wean ourselves off the fossil fuel source and stop burning fossil fuels in the manufacture of our products. There are factories in the UK today, manufacturing factories, textile companies. There's one in particular in my mind that I know is already at over 70% renewable energy. All their processing. No more fossil fuel burning for energy. That's a very important thing to mention. But there is a scenario, as I've mentioned here, where we could actually accelerate the impact of our industry on reducing emissions in a very positive way, where we could be sequestering carbon, keeping it in our fibres, in circulation for as long as possible, and get closer to this aspirational net zero position. And with that in mind, we're leading with two other institutions at Exeter and Northumbria, the Network Plus programme, which is taking a very scientific, evidential-based approach with hardcore environmental scientists involved to get a data-driven baseline for our industry. And I'd love to talk to you about how you could get involved in this, because textiles runs through me like a kind of Blackpool rock. So this program is here to help, not to pontificate and finger wave. I see this as a practical way of working out exactly where we are, with no greenwashing, no marketing. I am from Yorkshire, very pragmatic. Once we get to that point, we can be really clear about what interventions we need to prioritise and then get it done. Ladies and gentlemen, thank you very much.
Thank you, Steve.
I didn't expect this bit. Thank you.
We're not going to sing. Questions from the audience. I mean, it's fascinating to see what the future might look like, but I'll start the first question, if I may. And you and I have discussed this in many different ways before. What are, and this is an impossible question to answer, so my apologies, unintended consequences? We're dealing with unintended consequences now of the textile industry in the past. How important is it that we try and think that through to the future?
Can you just clarify what you mean by unintended consequences?
So if we moved to a completely bio-based polyester system, what are the potential negatives?
Okay, so I mentioned one of them, which is competing with food. We really don't want to do that. We also have to remember that transporting bio-waste over long distances is probably not a good idea either. So we'd probably be wanting to use bio-waste generated locally in this country, or certainly not on the other side of the world, or Brazil, or wherever. I've only mentioned GHG impacts as well. There are other impact categories that we need to bear in mind too. Water, fertilizer, soil conditions, ecotoxicity. There are other things to bear in mind. But this is why the thinking is that we need to move towards bio-waste, not first-generation waste. And the other big question is around where these biorefineries might be sited. This is something which already goes on, of course, to produce fuel. The food industry uses fermentation-type processes as well to make various foodstuffs in the UK. But all of those do have emissions too. There is also, just to mention, it's not an unintended consequence, it would be a deliberate action, is potentially carbon capture on these sites too, because you've got control of where the breaking down of the material is taking place. The other thing to say is, if we are burning the bio-based material at the end of life, incinerating it, then we send the CO2 emissions straight back up into the air, regardless of the fact that it was a bio-based source in the first place. Yeah.
Questions?
University of Westminster, Nicola Mansfield. I'm quite aware that as an ex-buyer and retailer in the industry, that we're quite dependent on blends. And I saw a product that was 28% cellulose blended with a very large retailer on the high street. What would you say to brands and fabric manufacturers who blend for price or blend for performance?
They're two quite compelling reasons to blend, aren't they?
Yes.
Performance and price. So if I were to say don't blend, then the product wouldn't perform as well, and it would be too expensive to buy, then it wouldn't be an attractive response. I think this does come down to the work of the work that's going on around collection and sorting, and getting materials separated. Clearly, there is a very important question about the way products are designed in the first place, which I think is what you're alluding to, and I agree with you. There are situations where we're making compositions overly complicated, which then has an impact later in terms of enabling recycling after reuse. So it is a tricky one. Blending is part of the toolbox, isn't it?
Well, it's performance, isn't it? If we didn't have lycra or a bio-based lycra, we'd have very different outfits.
Yeah, exactly. Yeah. This is why I tried to bring up this issue of practicality. Can we manufacture using our infrastructure that we already have? Imagine if we couldn't, how long that would take to resolve. And do the materials we're using have the necessary physical properties to be relevant? So it is a challenge, I agree with you.
Thank you. There's another question here.
Tim Cross from Project Plan B. We're bringing the first polyester recycling system for post-consumer textiles to the UK. It's in a joint venture with the Salvation Army. And I think that it's exactly the technology that you've described for us today. So it's really exciting, and we look forward to working with you on that. My question is, do you think that bio-based polyesters can be recycled at the same time, in the same batch, as oil-based polyesters? Or are we going to need to separate the two?
Yeah, thank you. From a scientific point of view, the materials are identical. So provided we make those bio-PETs into fibre-grade spinnable materials, so that we can spin them using the melt spinning systems that we have, in my mind, there's no reason why we wouldn't be able to recycle them together, because they are chemically identical.
I think that's going to be very, very useful.
Another question there.
Mark Price from Torre Textiles. So we already make the bio yarn, and we'd like to work with Plan B, and we can make textiles, and then you can test if we can recycle it along with the oil-based.
Brilliant.
In a minute.
Brilliant link.
Networking at its best. Parik, you had a question?
Hello, Parik Goswami, University of Leeds. Oh no, University of Huddersfield.
Sorry. Can I just say this is Parik Goswami from the University of Huddersfield?
Sorry for that. Steve, a bit of your thought on same material blending. So I'm alluding to the project that we did in 2017, where we can use the same material with different crystallinity for blending. Do you see that might be a way forward to aid recycling in the future?
So that comes down to formulation, doesn't it? And yeah, I think yes. I mean, again, I always come back to because of my engineering background, I always think to myself, what are we trying to achieve here? So as long as it's aimed at a specific product or range of products, then that's another tool in the armour, isn't it, I suppose? Yeah.
Any more questions? There's one at the very back.
Hi, my name's Ruth. I work for a technical narrow fabric weaver. Firstly, I'd like to buy some bio-based polyester, please. And secondly, we use about 10 to 15 tonnes of aramid fabric per year. Is there any way of recycling or regenerating an aramid?
I can't give you a quick answer to that question, unfortunately. That is a very chemically stable material, as I'm sure you know. I definitely know there are people mechanically recycling it, and there are some big developments going on in mechanical recycling as well. So the idea that what you produce in mechanical recycling is necessarily inferior to the first used application, I think, is questionable in some cases. But chemical recycling of aramid is, well, I don't think that's commercially something that's going on at the moment. With the access to the academic database I have, I think I would find some examples of people who are attempting it, but I imagine it is quite resource hungry.
Thank you.
Just going back to the first part of that question, Steve, when do you predict that bio-based materials will become available on a large scale?
Oh dear, prediction. Did you say this has all been recorded? Oh. Well, I think I'll come back with a caveat. I think that the first thing to mention is that we are not the only people looking at this. The packaging industry is a major driver of developments in bioplastics, bio-based plastics. They have even larger issues than we do, as you probably are aware. So that's driving increased demand in itself. I think the other thing is, I mentioned that 30% or thereabouts a difference in price for the bio-PET, fossil-based PET, those materials. You know, carefully considered incentivization, financial incentivization, could narrow that difference, and that could have quite a large effect on people's willingness to invest in scaling. So I go back to this point I made before about the playing field. The playing field that we're working on at the moment doesn't encourage these types of decisions to be made because they have a financial penalty, but it doesn't need to be that way.
Thank you, Sir Jonathan.
Jonathan Portal, Cloth Workers. Steve, absolutely fascinating. Your talks are always completely mind-blowing, and this is no exception at all. I was fascinated by your idea of a cycle that returns the product into the ground, rather like the oil reservoir that you used as an example. So my question is, given and you also started off by talking about end-to-end, a product, we should consider the product end-to-end. So my question is, how is the measurement of the impact of one of these end-to-end products and the way you were describing, how is that going? Is it possible to measure the impact on the environment of an end-to-end product? And I suppose the reason for asking that is that the way you were talking about it, you know, it's a bit of a roller coaster ride. It's a fantastic benefit, and then all of a sudden there's all these extra costs and problems and potentials and everything. Of course there is. You're halfway through developing it. Is there a way of measuring the end-to-end so that we've got a simple way of working out, you know, good, better, or bad?
Well, I assume. Thank you, Jonathan. I assume you're referring to the environmental impacts, are you? Or yes, yeah. So, what I laid out there as a sort of scenario, and as I said before, I'm not advocating. We're thinking about lots of different scenarios for the long term. What might work realistically? What is completely academic? You know, these are the things we've been thinking about. So this is one scenario. So that type of scenario does lend itself to life cycle assessment. You can do the measurements and do the calculations, and that comes down to the assumptions that you make in the normal way. But this idea of creating a resource effectively for the future until recycling technology catches up, is interesting if the material's not degrading in the process, which polyester shouldn't do in a landfill situation, or entombed within a concrete case. It does sound a bit blue sky, I admit, but who would pay to do that? But if we're not turning off the tap and the flow is continuing to leak these materials into the environment in unhelpful ways, we know we can recycle that stuff if we collected it and got it into the right place, use the right sorting technologies.
That's brilliant.
That's the point.
Unfortunately run out of time. Thank you very much indeed, Steve. For balance, other textile academics are available. Many of them are in the room. But thank you, Steve. Fascinating. Thank you very much indeed.